All right, let's start with some announcements. I apologize for a couple minutes being late, but let's see, we have an assignment due on Wednesday. You should be looking for another assignment early to mid this week. Anyway, so another assignment coming. You'll have a study guide by the end of the week since we're on week 5, coming up on next week's exam. They come like candy in this class. We can tie that to Halloween if we want to. But that's basically what's happening here. I did also reveal that first project. As you find yourself with a little bit of time, it's probably worth getting started on that because we all know how the end of the quarter comes way sooner than we think it will. And you don't know what all the rest of your classes are going to be doing at that point, or maybe you do. But yeah, you don't want to have this all happening at the same time. Questions on anything before we dive back into our non-deterministic pushdown automata, finishing up that unit? We were talking about deterministic pushdown automata. All right, the example we were looking at, we said that we were trying to show that the non-deterministic pushdown automata and the deterministic pushdown automata actually represent different language classes. And to show that, we were looking at these couple of languages and asked, are the first and second context free? And we found that we were able to generate a grammar for both L1 and L2. And then we defined the union of those languages as just one more grammar production. We said we're going to have a new start non-terminal that can be broken down into either the left-hand side or the right-hand side, where the left-hand side was the grammar for L1 and the right-hand side was the grammar for L2. So we know by the definition of context-free languages that this union language is also context-free. The issue that we ran into, however, was trying to deterministically parse this because we found that, great, the string starts with an A. Are we in L1 or L2? And we could not make that distinction at that point. We see an A, and well, both L1 and L2 force starting with A's. But in that grammar, we needed to make a decision about, do we go down the route of S1 or down the route of S2? Are we trying to match this string to L1 or L2? And the answer is it could be either. This is why non-determinism is useful here. You can just explore both of them in parallel. But we need that non-determinism to be able to map this language, to be able to accept or reject this language. We can't do it deterministically with a single pass from left to right. So this becomes a very easy proof that NPDAs and DPDAs look at different language classes. So now just kind of thinking in general, abstracting this idea, what are the kinds of languages that a DPDA could accept? Or what are the language of classes that an NPDA could accept that a DPDA could not accept? Does it go beyond just these union languages where there's ambiguity at the beginning of those strings? Are there other rules that we could generate? I call this a very easy proof, but this is really just intuition. It's not actually a complete mathematical argument. I try to strip out the actual proofs in class, though. Questions on that concept? Do we have an understanding of the differences between NPDAs and DPDAs? What did we say were the transitions that were allowed in DPDAs? What was that concept of determinism in a context-free state machine? Remember what that rule was? We allowed for lambdas somehow. Yeah.
You manipulate either the stack or the input string, but
yeah,
you have to do either. You can't do either.
Yeah. So there needs to be some distinct pair in this tuple now of the character that we are reading and the top of stack character that we are manipulating. So we can only have one transition out of each state for that tuple rather than just individually. So we can have two transitions out on an A as long as they manipulate different top of stack characters. what would we have to do to our concept of a grammar in order to be able to accept just deterministic context-free languages? So we've now talked about how context-free grammars can be parsed efficiently. We went over the CYK algorithm that gave us a cubic time algorithm that allowed for that, which was great. Deterministic context-free languages are even nicer than that. So because of this, at any particular state in a DPDA, we don't need that level of parallelism that we needed in an NPDA. We actually can deterministically parse from left to right in a single pass. So it's always linear, which is great. If you want to think of it visually, you would have the input, and don't worry about the name of sentential form. That's just the name of the production that the right-hand side of a production is called its sentential form. So in a single pass, you've matched something on the left-hand side, and there's this non-terminal, and non-terminals match what we haven't seen yet. Because of this, it's exactly like parsing a regular string in a regular language with any kind of DFA, except that now we can be making those stack transitions. So you can be thinking of, we have a stack along with us as we do a regular grammar. So what does that allow us to do if we now have access to a stack that we can push to up from? It actually is a simple grammar. So when we talked about simple grammars, the rules that we specified for a simple grammar map directly to what a deterministic pushdown automata can accept. We know this because the way that the simple grammar worked, there's only one choice of production to apply at any particular step, which maps to the exact logic of, from a DPDA, there's only one transition that we can take from our current state. I look to have not animated this one slide, the last couple slides correctly, but let's give you a quick rundown of this. So basically what's happening here, we can use this concept of a simple grammar to try to now parse even more effectively. The question now is, how many characters ahead do we need to look to know for sure which production to take? Because there's a little bit of a search when you can consume the same character and we don't know which top of stack character we need to now go down. You can imagine one is a push and one is a pop, consuming an A. Which one do we want to take? There's still ambiguity for that. But you can imagine that you could search out and say, with 2 characters ahead, is there anything, I see an A and then I see a B. Can that be done from both of these threads? So you can start to initiate a search from the current location. The goal of that search is to isolate which production you want to take for sure. And some grammars will be more efficient and say that no matter what the string is, a look ahead of at most one character will always tell you which production to apply, which one to take. And you might have some that says, no matter what the string is, a look ahead of size 2, a look ahead of size 3, a look ahead of size 5. There are other grammars where there is no such look ahead that you can make. So your second project has to do with this question of, can we simplify CYK and its cubic runtime complexity to be able to handle particular grammars where we can do a look ahead? It represents some kind of deterministic context-free language. We can do some kind of look ahead to figure out, can we actually parse this in linear time rather than cubic time? So in the last week or 2 of the class, we're going to come back to this idea of LL grammars, left to right, left post derivation, and we will actually get a chance to implement this and see how it's done. Very important part of the actual compilation, the construction of a compiler. So to give you an example of this, is this grammar an LL grammar? We have capital S arrow, capital S, or a capital SB, or AB. In order for it to be an LL grammar, we have to be able to look ahead some number of characters and know which of these productions to apply. And the look ahead for these characters is in the actual string. So we're trying to look ahead. The full string is now like AABB. If we look ahead, since we haven't started parsing this at all, we'll look 2 characters in advance. The first character, the second character, we see AA. Looking at this grammar, are there any sequence of productions that would create ambiguity to be able to produce that AA? So let's say we can select A capital SB, but if the full string is AABB, if the full string is AABBAB, then we have to select SS. We can't select ASB to do that. So that tells us that even with a look ahead of 2 characters, there exists one possible pair of strings that start with the same 2 characters, where one of those strings wants to first apply this production, one of those strings wants to first apply this production. So we can't say for sure with a 2-character look ahead what is actually which production we should apply, which is bad from compilation because we need to be able to answer yes or no to is this program in this programming language? We can't have that ambiguity. So either we have to apply CYK, or we would have to say, is there a longer lookup that we could use? If we could look ahead 3 characters, if we could look ahead 4 characters, but what would distinguish this from a look ahead of some constant number of characters, and there exists no number of look ahead characters that we could make? It's always possible to have that ambiguity.
Scale to look up based off how many non-terminals are in.
Not really. It's a good idea, but it doesn't really work quite as well as you would hope. So you can continue this logic, but the solution here is it doesn't matter how far out you look. There will always be 2 strings you can select that change the production you want to start with. So because of that, this grammar can't have an efficient parsing for it, which is kind of frustrating. So if a grammar is not LL, you may be able to convert it into one that does have a better form that is more easily parsable. So is this grammar equivalent to that grammar? And the answer is basically, if you just allow this second production now, we can basically just now say, this ends it, and now we can terminate an S in some capacity. Great, we have an equivalent grammar to this, and now this is in fact an LL1 grammar. There's only one production to pick if we see an A at first. And that's really interesting to think about. Questions on kind of the concept of an LL grammar? We'll dive into this in a lot more detail at the end of the course. Just wanted to sprinkle out here's eventually what's coming on the horizon. The application of it, you can define most programming languages with LL grammars, which is incredibly cool. If you're designing your own language, you want to be thinking about when this language is parsed, where is the associated ambiguity in this? Can I get rid of it? If you can, then you have a very parsable language. If a language is parsable, then its compiler will run quickly. If its compiler runs quickly, there are applications for it. But it tells you how much thought has gone into the languages that we use just to make sure that it's as efficient as possible. There's someone out there, many people out there, making sure that they're going and finding those optimizations so that our programs run faster. Knowing how that works is pretty important. Last minute questions on this hint of an idea before we move on to what we're all dreading, what we saw at the start of class.
If you go back to the previous slide.
Yeah. Any other questions while people are taking down the last few notes? think I've successfully done this, but we'll try one more time to successfully motivate why we're going back to a pumping lemma. This is what people are discovering that they want nothing to do with ever again. Probably. Get everything you need, Simon?
Yeah.
Awesome. So we're going to refresh ourselves on the pumping lemma for regular languages because it's really important to know this going into this topic. This topic is not as bad if you understand it, and it is worse if you don't understand the pumping lemma for regular languages. So we found that regular languages had some kind of repetitive pattern. To generate an infinite language, we needed some kind of loop in the structure of the DFA that accepts it. In order to prove that a language isn't regular, we just had to show that, all right, for any possible size DFA, there must be a loop somewhere in this. That loop must come within the first number of characters in the string that's equivalent to the number of states in the DFA. So we can proceed by a proof by contradiction. Assuming the language is regular, we assume that there exists a DFA for it. And then we show that, sure enough, you choose a string, based on that string, you say, we're gonna pump the middle section of that loop section of that, some number of times and try to generate strings that aren't in the language. If we can do that for every possible length that that loop could be, then that is a proof that this state machine could never have existed in the first place. And a language is not in the class of languages that that kind of state machine can accept. Because looking at state machines in context-free languages is so gross and ugly, instead, we're going to be thinking about this through the grammar lens. So we're going to latch onto this concept of a context-free language to show what is not a loop, but it is recursion. So hopefully people feel really good about converting iterative logic into recursive logic and recursive logic into iterative logic. I think that will help you to understand what's going on here. Let's start with just a list of differences. Just to get a sense of where we are at the moment. I know this assignment isn't due for a couple more days, but if I had to ask the class, how do you feel about applying the pumping lemma to the kinds of questions that you've been asked or we've shown either in class or on the homework that you've seen so far? No issues at this stage. Give me more of them and I feel like I'd do fine. I kind of get a sense of what's going on, but I struggle to be able to produce it, and something like no idea what's going on. So, excellent. We're all over the place. What that says to me is if you are feeling like there's some iteration to do on this, I will need to see you in office hours at this point because I have lots of ways to think about it. I would like to tackle this from your perspective. What are your challenges? What are your struggles? And I can use that to target some way of helping you to understand it. But we're going to want to understand it before we get too deep into this. So today would be a great day for that. All right, so we've already said most of these things. To be able to produce an infinite number of strings, have to have some way for a DFA to loop back on itself. The equivalent logic in a grammar, however, is that there is a loop in terms of we go from a non-terminal via some expansion, we produce that non-terminal again. So rather than thinking of it like a loop, we're going to think of it like recursion because that's what's happening. We're defining something in terms of itself. In order to generate an infinite context-free language, there must be some way to do this in a grammar. To go from a non-terminal and via some number of productions, generate that non-terminal again. So we would have something like the non-terminal A via some number of productions produces some substring V that comes before a new capital A and some substring Y that's going to come after that. So we've gone and recursively defined A in terms of itself, possibly producing a prefix string and possibly producing a suffix string in the process. Similarly, that non-terminal can now terminate. Basically, we can go from this non-terminal to a complete string without reproducing this particular non-terminal. So it seems very much like this concept of the DFA, where we had some initial state, and at some point we get to a loop, and somehow from there we get to a final state. So we had the ability to get to the loop, we had some number of iterations of the loop, and then we had some way of getting from the loop's termination here to the end to accept. So we broke this down into what we call X, which was going from the initial state to the loop, Y was the iteration of the loop, and Z was getting from the termination of a loop to a final state. Here, there are two important things to think of in terms of a grammar. We have the way to recursively define a non-terminal in terms of itself, and the process to terminate from that non-terminal that does not recurse. So we have the base case and the recursive case, as you have seen in every other class that's utilized recursion. The base case allows you to terminate the string and produce some string that's in the language. And the recursive case says some number of times we can redefine this character in terms of itself. Questions on anything so far? Do we see how that's kind of similar to this idea? Maybe. Lots of quiet. Maybe how we feel about that? Get a sense of where we are? Starting in a better place, a little bit better. All right. This allows us to produce an arbitrary number of strings via that recursion. We can produce X. The first time we see non-terminal A, we just find a way to end the string. Maybe let's give you an example of this. Let's say very simple language. We've already done this one, A to the N, B to the N. But now it's as short as possible, basically, to be able to say we can get from this non-terminal back to itself by just going S arrow A S B, and we would continue this process, but we have now recursively defined S in terms of itself. In another derivation, we could say this just becomes nothing. S becomes the empty string is accepted. So this would be the equivalent of this X. If we don't iterate the recursion and we go straight to the base case without doing any recursive process, then that is just this X. If we instead iterate the S arrow to the ASB and then go lambda, then this would be the equivalent of VXY. And now we can see that we could apply this twice. And if we apply it twice, we get VVXYY. Here X is the empty string, B is A, and Y is B. And we can now break this down in terms of a grammar in ways that produces just X, VXY, VVXYY. The number of V's and Y's you would have would map to that A to the N, B to the N. N is the number of V's and Y's that are here in the string. So we're using now a recursive definition to do this. Doing okay so far? Half nods, half stares. Excellent. All right, two big differences. We're pumping two parts of the string. That's weird. Instead of X, Y, Z, X, Y, Y, Z, X, Y, 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 Z, the pump occurs on either side of this X. This pump can also occur anywhere, rather than the way that the regular pumping lemma said it was one of the first M characters of the string. We can no longer rely on that assumption. So that's just gonna make this just a little bit more challenging. Pump twice. So let's take a look at what a construction looks like for this. And what rules we do actually have to work with. We can start any pumping lemma for context-free languages very similarly. I would still state something like, let L be an infinite context-free language. We can say there exists some positive integer M. Now M, instead of representing the number of states in an associated DFA, you can think of M now representing the number of productions in a grammar. So there exists some positive integer M, the number of productions, and a grammar that accepts this infinite context-free language, such that any string in that language can be decomposed in a way that we can now show is in the language. We're going to decompose it into 5 pieces instead of 3 pieces. We're going to call this UBXYZ, since we use W for strings. Things that we know for sure. 1, the length of VXY is less than or equal to M, the number of productions in the grammar. And the length of the recursion, V and Y, is greater than or equal to 1. This sequence shows us exactly what this is like in terms of the regular grammar. So we know we start at a start non-terminal, but we need to get to the character that is recursed. So this process of going from this step to this step is really just getting us to the recursion, kind of like getting us to the loop. It's what's not interesting about the grammar before we start the recursion. So again, this part is equivalent to the X portion that's going to get us to the loop that's going to get us to a final state. So here was X, there was Y, here was Z. This U is mapping to this X. This Z is mapping to this Z. So we're creating the structure of here is the string, what comes before the first pass of that, because this can be unique. Again, I don't know if that makes sense, but
You have multiple entry points into the recursion. Everything.
yes, but it's also you generate some things before you start that recursion. How do I want to show that? You're generating parts of the string before what gets repeated through that recursion is recursed. So maybe we have something that produces maybe we produce something like this. And what's going to get recursed in the middle of this is going to be some number of copies of something else. But this U and this Z are one time at the beginning and end of the string. Eventually, there's going to be this recursion point in the middle of the string. And what we care to produce here is this V and this Y around it, because that's what can be done a bunch of times. So let's say we want to say all strings consisting of A's, B's, C's, and D's that have exactly this prefix, exactly this suffix, and in the middle is some number of D's. Maybe it's even an even number of D's, just to make this a little bit easier. So now we would specify that V and Y is going to be what happens when we go from one iteration of this recursion to another. So every time we went from this A to this A, we'd be generating an extra D in front and an extra D in the back. So we would say something like, now we're going to produce this and that. That is one instance of that recursion. Now we could do it again. Do it again. And what's still in the middle of this is still the same A that eventually we need to decide how to get rid of. And maybe the middle character is a single E. I'm just trying to make this as have each step to this have something substantial to it. They can all be empty. But in the middle of this, we would say there is some production like A arrow E that allows you to put something in the middle of this. And that would be what terminates the string. So it's really 3 steps. What is the one-time front and end to the string before the middle recursive section? What is that middle recursive section? And then how do we get from that middle recursive section to terminating the grammar without any more non-terminals, such that we now have only terminals, something that's in the language associated with this grammar?
So the U and the D values that you're talking about, here, there's nothing specified in the constraints, so can they be empty?
Yes, same with any of these. Yeah, any of these can be empty. So the recursion could be only in front, only in the back. Everything that comes in the forward and back, anything can be empty, basically. But we want to be able to recurse in the middle, so we need to allow for the extra characters in the front and in the back. I look like I ruined your weekends. That's the general look in the room. What have I done to you? So this tells us now that all strings u, v to the I, x, y to the I, z are in the language. That's what we can really conclude from this process, is we know that we're recursively defining this v and y as the before and the after in a single instance of this recursion. So that tells us that all of these strings repeating v and y an arbitrary number of times, because that's just iterating this recursion an arbitrary number of times, all of those also have to be in the language by definition. Does that make sense? Looks like it is a little bit yes, mostly no. I kind of want to give an example. Actually, I have a visualizer. Let's use this visualizer. Here's how I like to think of it. So we have thought of grammars as nodes in a tree before. So you can imagine the root node of that tree being the start non-terminal in the grammar. What gets generated as we get to our first non-terminal that is going to get recursed, there's going to be, in the process of getting there, there's going to be some portion of string that is generated before and after that particular start non-terminal. That before part of that string is going to be called U, that after part is going to be called Z. Then we can define the recursion of how do we get from this non-terminal back to this non-terminal, and whatever characters we create on either side of this is now inside of U and Z. We can produce some characters that we're going to call V and Y. Since we do this an arbitrary number of times, we can define S getting to A, doing this 0 times, and then A going to X. And when A goes to this terminating value, whatever characters it produces here are that. So you can imagine going from S to A, skipping this, and going from A to termination. And that would generate the string U, X, Z, or U, V to the 0, X, Y to the 0, Z. If we went from S to A back to A, and then A to termination, we would get U, V, X, Y, Z. If we went from S to A to A to A again, and then terminated from there, we get U, V, V, X, Y, Y, Z, because we produced this chunk twice. So it's just defining that recursive relationship and how we can now go from a start non-terminal in a grammar to termination and produce an infinite number of strings via a single recursive definition. Questions on that? Very abstract. But I really like this visualization. I think it helps a lot in terms of how is this actually being broken down? How is it producing strings on either side, partial strings on either side? Feel free to tune this out if this hasn't been particularly helpful to you. But if we're thinking about this in terms of the game that I had designed between two players for the pumping lemma, then how would that game change for the context-free pumping lemma? It's the first expansion set. The first DLC. I don't know who's buying a game based on the pumping lemma.
People who really.
I wouldn't spend my money on a game about the pumping lemma, but hey, if there's that demand out there, I'm sure there's at least one person out there who would buy this game. Right? So we said that for the regular pumping lemma, player one picks the number of states in the associated structure that represents this. Player two then picks a string with length at least m. Player one gets to choose the decomposition, but now instead of it being X, Y, Z, they produce the definition of the recursion. So they get to pick VXY, but the length of VXY has to be less than or equal to M. Because just like with states and getting back to states, if M represents the number of productions in the grammar, then we can't apply different productions more than once before we generate a production that leads back to a production that we've already seen before. So it's very similar to the argument about the number of states in a DFA. Because if you only have two productions in your grammar, you can apply the first production and then the second production. And if there exists recursion that allows you to generate an infinite number of strings, then we had to have gone back to a non-terminal that we've seen before already, because there are only two productions in the grammar. So that becomes a nice grounding point in reality. We then said player two chooses the value of I, such that we can now show that u v to the I, x, y to the I, z is not in the language. And again, that's just an instantiation. So what you want to really go prove for something like a homework problem or on an exam is that you can set this game up in a way such that player one cannot win. So you provide the argument that according to this game, player one is dead in the water before they begin. It's really just tic-tac-toe, but a much more complicated tic-tac-toe that no one wants to play. Kind of like tic-tac-toe when you become an adult. So let's see if we can quickly see an example of this. Here's a language, A to the N, B to the N, C to the N. Wow, we've attached a whole letter to the end of our A to the N, B to the N. There's something special about context-free languages, introducing it with A to the N, B to the N, and closing it with A to the N, B to the N, C to the N, that feels interesting, but also revealing a little bit. So any intuition when you look at this language? The goal is to be able to use a stack to be able to count N. Why is that impossible? Or why are you going to struggle with that? I rephrase this in terms of write an algorithm that maps a string to A to the N, B to the N, C to the N. You get one pass left to right, and you get one stack that you can either push anything to or pop anything from.
After you're done writing these, there's no stack memory left.
Yeah, you can map the A's and the B's together. You could map the B's and the C's together, but as soon as you map the A's and the B's, you've lost track of how many A's or B's there were. So you can't map and ask if there are that many C's. Or you could ignore the A's and then map the B's to the C's, but then you have no way of saying however many A's I've skipped over, because you get a single stack. If you had two stacks, now you'd be fine. But a single stack, you can't do it. Convince yourself of that by thinking through it for a bit. And then think about what string should we pick here to proceed by this proof by contradiction. Any thoughts on the string we should pick?
Just throwing out the A to the N, B to the N, C to the N.
Gorgeous. Why?
Well,
was if we're defining,
V, X, Y now. You can show, so that V, X, Y is just A and B, and then C afterwards, or you can just put it as A.
Okay, so yeah, we don't know where this recursion is going to happen. It can happen anywhere along this string, but we know that the recursion's length is bounded by M. So that tells us that we may be recursing only A's, we may be recursing only B's, we may be recursing only C's, but now there is the possibility of recursing A's and B's, or B's and C's, because it's really a sliding window of size M that we're moving across the string now, and we're not forcing it to be the first M characters. That makes this a lot more work. It's not significantly harder, it's just more of it, because now we have to come up with counterexamples for each possible alignment of that window. So let's say player one picks this breakdown, this recursive breakdown VXY. They have options now. They can pick something that is all A's, they can pick something that's A's and B's, pick something that's all B's, pick something that's B's and C's, pick something that's all. I will spoil this and just say, if we pick any I greater than 1, this won't work. But let's actually break that down and ask why. So I pick all A's as the breakdown for VXY. Luckily, this is as difficult now as the regular language pumping lemma. We just have to say, if we set I to 2 or more, we're going to be adding A's into this string. That gets us A to the M plus the length of Y, B to the M, C to the M, which is obviously not in the language because there are more A's than there are B's and C's. We've broken the rule that there have to be an equal number of each. Done. And you can use very similar logic if someone picks all B's or all C's. But what happens if we pick something that is in the window of some A's and some B's? 2 ways to proceed, yeah.
If we look at the grammar rule, so even if we can produce only A's and B's, we have to start with only A, only C at the end, or only A at the start. And then there's gonna be essentially more A's and B's or more B's and C's than A's or C's.
Yes. So if you pump something in the middle of these A's and B's, we know that we're going to be adding at least one, either A or B, to the string, if we set I equal to 2. So to do that, then we either end up in the case where we already showed adding some A's doesn't work, adding some B's doesn't work. What if we add both A's and B's? Well, then the number of A's is different from the number of C's, or the number of B's is different from the number of C's. So you can attach yourself to that concept and say, now we've broken that law. And similarly, you do the same thing for B's and C's. So basically we have these 5 options. So this breaks down into a proof by cases with 5 parts. But those 5 parts break down in ways that are very similarly explained. So I would even group the all A's, all B's, and all C's together in a proof and say, if you pick a sliding window of size less than or equal to M that's over a single character, then any I is going to pump that since there are more of that character than the other characters. If you pick A's and B's or B's and C's, you pick A's and B's, you want to compare to C's, you pick B's and C's, you want to compare to A's. Saying I'm not pumping any of those and I have to be pumping the others. Therefore, there is no way with an I greater than 1 that I can possibly produce another string in a language, let alone more than that. The other thing you could do is show, this one's a little bit harder, but if we had some number of A's, some number of B's, and some number of C's, and you wanted to repeat over something in the A's and B's that would be breaking the need for all A's to come first, then all B's, then all C's. So if we picked something like this AB as a Y, then we could pump this a number of times to get A, B, A, B, A, B, 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 C, C, C. We can look at this section and say that does not adhere to the form of the language that we had in the first place. So I would not do that. That proof is gonna be a little bit harder. But for the most part, there's something fairly easy to attach yourself to be able to show that no matter what, once you recurse, you're okay. But it actually looks almost like the same type of proof. You just have to now think of it in terms of grammars and recursion instead of state machines and transitions between states. How are we doing? Does that example make some sense? Some people giving me information, a lot of people saying, how are we doing? Maybe actually give me some thumbs so I get a sense of where we are. Okay.
Can I ask a clarification?
Yeah,
question?
absolutely.
Did you say like for all the stuff, for what player one can pick, we have to debunk all of them? or
Yes.
just all of them?
Which is very easy if you leave this M uninstantiated. As soon as you instantiate it, then it becomes a nightmare. So don't,
Well, it's impossible.
yeah,
You eventually have to go to
yeah.
a variable case.
Well, you could also do an interesting inductive proof where you could show something like, this is true for a grammar of a single production. And if it's true for a grammar of size n, then you could produce something of size n plus one. So you could tackle it inductively, but that doesn't sound very fun.
What do you mean by unsubstantiated?
So instantiating M would be to say there's a value for M. And when I say M, it's a variable. What value does it have? Who knows? When I say let M equal 3, then what I'm doing is I'm saying that there is no grammar of 3 productions that works for this language. And that's not saying very much. There might be a grammar of 4 productions or 10 productions or 20,416 productions. So if we leave it as M, then we can make a general argument where if someone said, what about 20,614? Then you would have a counterexample picked already as part of your proof to say, let this string be A to the 20,614, B to the 20,614, C to the 20,614. We can proceed with a proof by contradiction to show that no such grammar exists of that size.
On an exam, are you gonna give us like a full grammar, and we take that full grammar to this,
Maybe.
or is it gonna be like?
It would be something that was very easy, because I would not, if something like this shows up on an exam, again, I could write problems that would take 40 minutes, and I can't do that and test everything else. So if this shows up, it will be a very simple one that I would structure to take 20 or fewer minutes.
Each question or like voting, like S goes to A, here's this, and then it could have just been like S has this non-terminal, and then person.
Last minute questions before we start some office hours? Or we go get some food or whatever else it is you'll plan next? Right. I will see you all tomorrow. Let's see, the exam is 2 weeks from Friday, so a week from the.
Yeah. It's really nice. Unlike the.
Plenty of time.